I'm going to do a run through on the experiment that we are going to be doing uh, in the next couple days. Let's see if my mic's working. All right, good. We got sound. All right, we got good. All right, cool. So we're going to do this experiment in 2 days from now, but I'm just basically jumping ahead to see if I can get ahead of the schedule. All right, so let's take a look at what we're going to do. We're going to do an experiment that is pH and color change. So whether or not something is acidic or alkali, like a base level, like milky or something like that. Um, uh, uh, what does the color change indicate? So again, another way to identify an unknown substance is to see what is its pH level. Okay, if you ever have a pool, you want to have the pH as neutral as possible, because if it's too acidic, it'll burn you, and if it's too alkali, uh, it's just not good, right? So let's go with it. All right, and let's see. Okay, so as always, Alexander, Riccardo. Some of you may have noticed that I forgot to put in the advisory aspect to it for a couple of the previous work. I have since fixed that. Um, I'm a dunderhead for that one, but yeah, I had to go in, and everybody that submitted a response, I had to go in there and personally put in their advisory. Imagine if I forgot to do it all week. That's 130 times four assignments. It's almost 500 times I'd have to do it. All right. So PA and color balance and color change. Previous lesson in chapter 5, of which we haven't done yet. Um, there's one called the universal indicator as a test liquid. The reaction between a universal indicator and one or more substances results in a color change. In this lesson, you'll see how acids and bases react with universal indicator and the color changes that result. You'll learn that the color changes mean and how to relate to a scale of measurement called the pH scale. You'll look at the reactions all the way down to the molecular level to better understand what pH measures and why it changes when an acid or a base is added to water. Okay, so let's rock this joint. All right. We're going to use a green solution called universal indicator. Universal indicator is a special combination of substances called pigments, colors that give the indicator its color. When certain substances are added to the universal indicator, it changes color. Here's the color chart for your universal indicator. It tells you whether a substance is an acid or a base, and also how acidic or basic the substance is. So it starts at 4 and it goes Roy G Biv. ROY uh, G B V, right? All right. So um, Roy G Biv. BV. All right. So it's kind of like the light spectrum. Red is 4, orange is 5, 6 is yellow, and that's acidic. 7 is greenish. 8 is hunter green or dark green. 9 is blue, and 10 is violet, indigo, purple, whatever you want to call it. Okay. So Roy G. Biv. All right. Let's take a look.
The green liquid in the cup on the left is made from a liquid called universal indicator mixed with water. Universal indicator has a special combination of substances called pigments that give the indicator its green color. When certain substances are added to the indicator, it changes color, which can tell you whether the substance is an acid or a base. The universal indicator has turned pinkish red in the citric acid solution, but in the sodium carbonate solution, it turns purple. Universal indicator has its own color chart, which can tell you whether a substance is an acid or a base, and how acidic or basic the substance is. In this lesson, you'll use an acid, a base, and universal indicator solution to learn about how acids and bases affect water, and you will learn to measure the effects with the colors and numbers on the pH scale.
All right. Cool. All right, what does the color of the liquid after the universal indicator is added tell you about the substance that was already in the cup? Level of acidity, um, Okay, the cup with indicator contains the universal indicator pigments dissolved in water. What does the green color of the water indicator solution tell you about water? It's neutral. The pH of citrus acid is approximately. Oh, I didn't catch that part.
Scale.
Where is that?
With the colors and numbers affect water. And you will
So
learn
that's
to
like
measure the effects with the colors
red,
and numbers on the pH
orange.
scale.
So it's like 4.5. Like I'll say 5. Sodium bicarbonate forms a blank when it's dissolved in water. That was the purple one, right?
Colors and numbers on the pH scale.
Right. So where's it at?
And you will learn to
Sodium
measure the
bicarbonate is
effects with the
purple,
colors and numbers
so
on the
that would
pH
be a
scale.
base, right? Right. So let's see, a 4 or lower, whatever. And purple is 10. I said 5 because it looked kind of orange. I don't know. I would have gone 4.5, right? Water is green. That's in neutral. Citrus acid is a weak acid. It's like vinegar. All right. In the video, a small amount of citric acid is added to the water before each drop is added to the next cup of universal indicators. So the citric acid solution is more concentrated and more acidic each time it's tested. So it should get more and more redder as it goes. Okay, so let's take a look. Adding increasing concentration of citrus acid solution to universal indicator. So it's green, and then it's going to get more orange as you go along. That's my hypothesis.
At the top left, we have water. At the bottom, we have 4 small cups of universal indicator solution. We will add a little bit of citric acid to the water and then add it to the universal indicator. First, the citric acid is added to the water and swirled to dissolve it. Now, 1 drop of this weak citric acid solution is added to the universal indicator. What is the resulting pH after 1 drop of this weak citric acid solution is added?
So it went from 7 to 6.
Now we'll add a little bit more citric acid powder to the water. One drop of the slightly stronger citric acid solution is now added to the universal indicator.
So now it
What is
went
the
from
pH
7 to 5.
of this slightly stronger citric acid solution? Finally, more citric acid solid is added to the citric acid solution and the cup is swirled so that the citric acid can dissolve.
So this one should be
We'll add
red.
1 drop of this strongest citric acid solution to the universal indicator.
See? It's like reddish orange.
What is the pH
All right, it's
of
red.
the strongest citric acid solution?
Okay.
As the citric
So it'd
acid
be like a
solution
4.
became more concentrated, the color moved from green towards red on the pH color chart.
Yeah.
And as the citric acid solution became more concentrated and more acidic, the number on the pH scale decreased.
All right. Nothing was added to the indicator in the first cup based on the color of the first cup. What is the pH of the indicator solution? 7. After adding one drop of acidic solution to the second cup, the pH of the second cup should be a 6, right? And then after adding another one to the third cup, it would go to a 5. And then to the fourth cup, it would go to a 4. And then we take a look at it, and that should be correct. 7654, and like a baller, I got it right. Right. So in the following video, a small amount of sodium bicarbonate is added to the water before each drop is added to the next one. So the sodium carbonate solution is more concentrated and more basic each time it is tested. So it goes to Starbucks a lot. If you caught that, that was funny. To help answer the questions below, take notes on the pH of the solution in each of the cup as you watch the video. So it's going to start out green, and then it's going to go dark green, and it's going to go blue, and then it's going to go violet. That's my my hypothesis.
The cup of clear liquid at the top left contains water. Below that is a small cup with a toothpick and sodium carbonate powder. The 4 small cups at the bottom contain green universal indicator solution. A small amount of sodium carbonate will be added to the water. The cup is swirled so that the sodium carbonate dissolves. 1 drop of this weak sodium carbonate solution is added to the second cup. What is the pH after 1 drop of this weak sodium carbonate solution is added? Another portion of sodium carbonate is added to the water, and 1 drop of this stronger sodium carbonate solution is added to the universal indicator. What is the pH in the third cup with a stronger version of sodium carbonate solution added? Finally, more sodium carbonate is added to the water. This will be our most concentrated sodium carbonate solution. 1 drop of this most concentrated sodium carbonate solution is added to the cup on the right. What is the pH of the solution in the fourth cup?
So like I said, green to purple. Yeah, so that's good. Nothing was added to the indicator in the first cup, so that should be a 7. And then after 1 drop, it'll go up to an 8. Well, wait a minute. Second cup, 7.5. All right. The next one would be like an 8.5, I want to say. And then the fourth one would be a 10. Okay. I'm just banking on that one right there. 7, 7.5, 8.5, 10. Cool. All right. All right. We're good. All right. To understand pH and how acids and bases work, you first need to look at an interesting thing that normal water molecules do when no acids or bases are involved. So proton transfer between water molecules.
To understand pH and how acids and bases work, you first need to look at an interesting thing that normal water molecules do when no acids or bases are involved. Each hydrogen atom in a water molecule has both a proton and an electron. The hydrogen atoms share their electron with the oxygen atom. Water molecules continuously move and bump into one another. Sometimes, when 2 water molecules come together, a proton from one hydrogen atom leaves its water molecule and becomes part of another water molecule. Only the positively charged proton moves. The negatively charged electron stays behind. So, these 2 water molecules become the ions H3O plus and OH minus. When these ions bump into each other, the proton from the H3O plus can move over to the OH minus ion, forming 2 regular water molecules again. Because protons go back and forth between the water molecules or between ions continuously, there's always the same amount of H3O plus and OH minus ions in water.
What?
Let's watch that again one more time. Here we start with 2 water molecules. The hydrogen is made of a proton and an electron. When the water molecules collide, one of the protons is transferred. It leaves behind its electron, so that water molecule is now OH minus, and the water molecule that received the proton is H3O plus. When H3O plus collides with OH minus, the proton can be transferred back, reforming 2 water molecules.
Yeah, that's pretty cool. All right. Take a look. Each hydrogen atom in a water molecule has both a proton and electron. The hydrogens share their electrons within the they share within the hydrogen. Oh no, oxygen. Hydrogen shares their electrons with the oxygen level. Water molecules continuously move and bump into each other. Sometimes when 2 molecules come together, a proton from one leaves its water molecule and becomes the other one. Only the positively charged proton moves, the negatively charged electron stays behind. When these ions bump into each other, the proton from the water molecule can move over to the OH. From the H3O molecule can move over to the HO molecule, forming two water. No, OH there. Boom. Got it. Yes. Did I get that right? Yes, I did. Okay, cool. All right. That was a quick understanding of it. After the proton is transferred, the water molecule that that now has the extra proton is called the H3O plus ion. The reason why the number of hydrogen atoms changed from 2, the subscript in H2, to 3, the subscript in H3, is because having an extra proton is like having an extra hydrogen atom, even though the electron did not come over with it. Remember that hydrogen is the element with only one proton in its nucleus, um, because one proton was added. There is one more proton than electron, making this a positive ion. All right. The water molecule that has lost a proton now has an extra electron, so it is called the OH negative ion. The reason why the number of hydrogen atoms changed from um, 2 to 1, the subscript H2 to 1, no subscript after the H means 1 hydrogen, is because losing a proton is like losing a hydrogen atom, because only the proton was transferred. There's one more electron than proton, making this a negative ion. H3O plus ion is called a hydronium ion, and OH negative is called a hydroxide ion. They are ions because they are not neutral, but charged molecules with uneven number of protons and electrons. And that is true. All right. So adding an acid increases the concentration of H3O plus and causes a color change. Spadoink. Let's watch it.
This animation will explain why adding an acid increases the concentration of H3O plus and causes a color change. The green area represents the universal indicator solution, and at the bottom we have one indicator molecule in an oval. It is surrounded by many water molecules. When an acid is added to the indicator solution, the acid donates protons to the water molecules. This increases the concentration of H3O plus ions in the solution. The H3O plus ions donate protons to the indicator molecules, causing the indicator to change color towards red. Let's watch that again. The acid will donate protons to the water molecules, which turn into H3O plus ions. The H3O plus ions donate protons to the indicator molecule, which turns red.
Okay. When an acid is added to an indicator solution, the acid gives up protons to the water molecules. This increases the concentration of H3O positive ions in the solution. The H3O positive ions then give up protons to the indicator molecules, causing the indicator to change color to red. All right. All right. So adding a base decreases the concentration of H3O plus and causes a color change. Let's do it.
This video will show why adding a base decreases the concentration of H3O plus and causes a color change. When a base is added to an indicator solution, it will accept protons from the water molecules, creating OH minus ions. The H3O plus ions and indicator molecule will donate protons to the OH minus ions, decreasing the concentration of H3O plus ions and causing the indicator to change color towards purple.
Okay. So when a base is added to the indicator solution, it takes away protons from the water molecules, turning the water molecules into OH negative ions. The H3O plus ions and indicator molecules give protons to the OH negative ions, this decreasing the concentration of H3O plus ions and causes the indicator solution to go towards purple. All right. There goes purple and red. Yeah, yeah, we're good. All right, adding citrus acid solution and sodium carbonate solution to the indicators. All right. So what colors are they going to go? Let's do this.
The cup at the top left contains citric acid solution. The cup at the top right contains sodium carbonate solution, which is a base. We have green universal indicator in the two cups at the center. The citric acid is added to the universal indicator solution. Notice what happens to the pH when the acid is added. Now we'll add sodium carbonate, which is a base, to this acidic solution. The base causes the solution's pH to increase from 4 to around 6. When we add more sodium carbonate base, the pH will continue to increase. The new pH is around 7. We have neutralized the citric acid by adding sodium carbonate.
Cool. All right. When the citric acid was added to the indicator solution, what color did the indicator become? It became about red. And what happened to the pH of the indicator solution? It decreased. And did the solution become more acidic or less acidic? It became more acidic. And when the sodium carbonate solution was added to the indicator citric acid mixture, what color did it become? Well, initially it was purple, but it did become green. And did it increase? Yes. Did the solution become more acidic or less acidic? Less acidic. And when a solution is added to a base, or a base is added to an acid, the solution moves closer towards neutral. It may not get there, it may go past neutral, but acids and bases tend to neutralize each other. So that's why when you eat something very acidic and you want to and it hurts your esophagus, your throat, your stomach, or whatever, you drink milk, and it'll knock it out. That's good. All right. There's the explanation that I just gave because I'm awesome, and then that's it. All right. I think that this one was pretty cool. I understand the color variances, and I would go with this one. I would do this one easily in a classroom. This one was pretty good. So hopefully this helps you guys out, and it makes it easier to understand this concept. So I'll see how you guys respond to it in a couple days. Deuces.